This will be our first lecture video about the subject Physics 70, Light Physics for Food Science and Technology. The learning outcome intended for this lecture is to analyze the dynamics of water activity in food through the various sorption concepts, molecular addition, adsorption equilibrium, time to reach equilibrium, food surface morphology, and moisture contents. Have you ever wondered how you can have crispy chips and biscuits, or nice tender brownies and landang that can maintain the texture of all its components? How can you avoid caking and clumping issues with ingredients, or determine if your product will be susceptible to spoilage? All these examples are controlled by water activity. Here, we denote water activity with AW. A stands for activity and W stands for water. If you understand how water activity works, you'll be able to understand and develop products that are stable and desirable to the consumer and can predict and prevent any potential spoilage. Water is an important component of nearly all food materials and plays a decisive role in dictating the physical properties, quality and microbial, chemical and biochemical degradation of food material. For most food materials, unless the moisture content is reduced below 50%, much of the water content is freely available to behave physically as pure water with properties such as vapor pressure equal to the pure water. As moisture content is lowered further, a point will be reached at which the water becomes less active in that it cannot act as pure water. For example, it cannot freeze or act as a solvent or reactant. In this state, it is considered to be bound water. The way in which water is bound to the internal structure of the food, the degree to which it is freely available to act as a solvent, to vaporize or freeze, or the degree to which it is chemically bound and unavailable can be all reflected by an ability to specify the water activity of a food material. The matrix presented in Table 1.1 attempts to illustrate the range of conditions under which water may be bound and the role it can play under each condition. So in particular, if we have a type of water that is dropping from the bodies, so we call this one as a water droplet that is adhering to a certain surface, and that this requires zero heat binding, and the binding type is actually non-stoichiometric. On the other hand, if we try to look at adsorbed water, so this is actually the case wherein you have water sitting on surfaces, but the case for binding is actually called as physicochemical, and the requirement for the heat is actually ranging from 100 to 3,300 joules per grams of water. The water activity of a food can be thought of as the equilibrium relative humidity of the food material. When a food sample comes into equilibrium with the atmosphere surrounding it, the water activity in the food sample becomes equal to the relative humidity of the atmosphere surrounding it. Once this equilibrium is reached, food sample neither gains nor loses moisture over time. So that means the water activity of that food is constant and it will never change through time. The equilibrium relative humidity described above comes about as a result of a two-step process involving transfer of water vapor between the food sample and the surrounding fluid atmosphere. So in this particular diagram, we have the interface of the food and the water molecules. So one step tells us that water vapor must transfer across the boundary surface of the sample in the form of adsorption or desorption, depending upon whether water vapor is entering or exiting in the sample. So in this case, desorption is the case wherein the water vapor molecules leaves the surface, while adsorption is actually the case wherein water vapor adheres into this surface. The second step involves diffusion or adsorption of water vapor into or out of the interior tissue structure of the sample. So diffusion is the case wherein the water travels within the sample, and absorption is the case wherein this water vapor penetrates the food. So as you can see here in this setup, when you place the towel in the glasses, the water from the first glass travels into the second glass by virtue of the two types of sorption. So we have water is being absorbed here, and then after absorption, the water is actually diffused to the second glass. Thus, the water here becomes lesser. So the same thing for this setup, wherein when the food is actually placed in the coffee, so the water vapor comes in or is absorbed in the food sample, and thus the sample expands through the help of diffusion. When the fluid material are attracted to the solid surface and begin to adhere to it, the process is called adsorption with respect to the solid. When the same molecules are already present on the solid surface and are escaping the surface being attracted to the fluid phase, the process is called desorption. For example, when a fresh moist food sample is being dried to produce a dehydrated product, it is placed in an environment of very low relative humidity. Under that condition, the free water molecules on the surface begin to escape into the relatively dry fluid atmosphere surrounding it in attempt to reach equilibrium relative humidity, and the food sample is undergoing desorption. Alternatively, when a previously dehydrated food sample is being rehydrated by being placed into a relatively humid environment or surrounded by water, the water molecules from the surrounding fluid will be attracted to the dry surface and begin to adhere to it in attempt to reach equilibrium relative humidity, and the food sample is undergoing adsorption. The rate at which this adsorption and desorption processes take place is governed largely by the physical and chemical characteristics of the surface boundary. For example, how readily the fluid molecules can either adhere or escape from the surface can depend upon special features of the surface physical structure, such as roughness, smoothness, and porosity. Beside physical adsorption, there can also be chemical binding that can enhance or interfere with the surface adsorption or desorption process, as shown in this figure. The term adsorption equilibrium refers to the steady state condition that is ultimately reached when adsorption and desorption are going on at the same time. This is a dynamic state in which molecules are leaving the surface while other molecules are attaching themselves to the surface in an adsorption process. Eventually, a dynamic equilibrium state is reached when the number of molecules leaving the surface and those attaching themselves to the surface is the same, and the number of molecules resting on the surface remains constant on the average. So that would mean that the time rate of approaching water vapors into the surface and the time rate of water vapor escaping the surface are equal. We have adsorption equilibrium. So that's all for our first lecture. Now, for the information of everyone, I'm using this main text reference